Hello, my name's Garth Johnson. I'm Professor of Rehabilitation Engineering at Newcastle University. And what I want to do in this first of two talks is to talk to you about the very basics of the biomechanical aspects of the shoulder. Can we think of shoulders as being hips up at the top of the body rather than lower down? No, they're really rather different from each other in a number of ways. The range of motion of the shoulder, we expect something like 180 degrees. We expect to be able to reach up to things on the ceiling and tie our shoelaces and reach our backs. The range of motion at the hip is rather smaller and we don't expect such large ranges. If we think about the forces in the joints, then we know from a lot of research that forces in the hip joint, even during normal walking, can be around 4 or even higher times body weight. Forces in the shoulder, from what we know so far, are probably little greater than about 1.5 to 2 times body weight. The function of the hip is extremely well defined. It is largely, we can say, that hips are made for walking. The function of the shoulder, as I've already hinted, is really much larger than that. We expect it to be able to position our arm in an enormously varied range of positions. Failure of the two kinds of joint replacements is also rather different. The wear problems of hip joints are very well acknowledged and have been researched in very great detail, whereas the problems of replacements of the shoulder can be associated with glenoid loosening because of the particular properties of the scapula, and with dislocation or subluxation for reasons that we shall see in a little while. So, from our shoulders we expect a large range of motion, and perhaps these sporting slides give a hint of just what we really do expect from this very versatile joint. Perhaps England would not have done so well in cricket and rugby had it not been that their shoulders were really so versatile and so well developed. So what are the anatomical consequences of this expected large range of motion? In the rest of this talk, what I want to do is to show how the shoulder anatomy is related to the functional requirements we've looked at, to show that this cannot be achieved by a simple ball and socket, as it is in the hip, but requires a musculoskeletal mechanism, and to show that this mechanism can only be understood by detailed biomechanical measurement and modelling exercises. So let's think about the shoulder skeleton and look at the key features of that. The first things we notice are that, first of all, the glenohumeral joint, the glenoid, is a very shallow saucer. It shouldn't really be thought of as a cup at all. It is much more akin to a saucer with some soft tissue labrum round the outside. And then, of course, the arm does not articulate directly with the trunk, but it is connected via an intermediate bone, the scapula, which itself can move on the chest wall to accompany arm movement. Why is it like this? Let's think now just about the simplest form of single ball and socket joint that we can, and look at the relationships between the amount of enclosure of the joint, its stability and its range of motion. If first of all we make an over-constrained ball and socket, so that one that would have to be assembled and in a particular special way, then clearly that will be highly stable, but it will have a range of motion limited by the amount of wrap of the socket around the ball. If then we go to just a semicircle, then we can see that the range of motion will be increased, but the stability will start to be slightly lower than in the wrapped over case. If finally we then look at what we might think of as an underconstrained, a socket which covers less than 180 degrees, then we can see we have a nicely underconstrained joint in which a large range of motion is possible, but at the same time it is easy, relatively easy anyway, for this joint to dislocate. If we look at these two conflicting factors, moving to the right of this slide, we have an increasing range of motion, whereas if we move to the left, we have increasing stability. To summarize this aspect of the design, what we're seeing is that there are two conflicting requirements. On the one hand, if we move to the right of the slide, we see how we can increase the range of motion by decreasing the enclosure of the joint, whereas moving to the left, increasing the enclosure, we increase stability but reduce the range of motion. So we have here two conflicting requirements. The first thing we might think about to overcome these problems is how might we increase the range of motion while maintaining stability, because of this, to overcome rather this conflict. Normal function demands, as we've said, a range of motion of the humerus around 180 degrees, and anatomically there is probably only one solution, which has arrived through evolutionary change, which is to move an intermediate bone, the scapula. So let's look at a little bit more detail about the role and range of motion of the scapula. If we have a fixed scapula, then we can see that as we've said, the range of motion is likely to be limited, but also the change of length of the major muscles, and in particular the deltoid, is going to have to be quite great to allow sufficient motion. If, on the other hand, we allow the scapula to move somehow in harmony with the arm motion, then we can maintain the length of the deltoid and overcome some of these problems of stability by having slightly more constraint at the glenohumeral joint itself. So how do we then cope with increasing further the stability of this joint complex? And it's at this point we have to think about some other muscles at the joint other than the deltoid. Those are the rotator cuff muscles. Coming back to our simple ball and socket model, we now have this very shallow socket, and we have the deltoid muscle pulling upwards, which is the major elevator of the arm, and we can see just in this next figure how that can quite easily encourage the ball and socket to dislocate from that upward force on its own. If we now add some forces acting downwards and medially, we can see that that is going to increase the stability of the joint, holding the ball and socket together. It's this force action which is provided by the group of muscles, the rotator cuff muscles. Looking at this anatomically, we can see how the deltoid goes around the outside of the joint with that line of action corresponding to our earlier simplified picture, and the muscles of the rotator cuff all tightly wrapped around the blade of the scapula, providing this downwards and medial force. So that is how the anatomy has evolved to provide this joint function of an elevating muscle and a set of muscles assisting stability. So we now have this anatomical solution which is allowing us a large range of stable motion of the shoulder. So we have a shallow ball and socket, potentially unstable. We move an intermediate bone, the scapula, and then we use muscles, and it's important to note here that it's muscles that do this, not ligaments, to maintain the stability of this now joint mechanism or complex that has been created. So let's now think about how, as engineers, we can start to look at much more detail about the mechanical actions of this joint complex, which we've seen has arisen largely from logical, biological and mechanical evolution. We should think now of the shoulder as an engineering mechanism. It's quite a complex mechanism, and think of that rather than it as a single joint. And here we just have a short video showing this accompanying motion of the scapula, because this is one of the key elements of how the shoulder is able to operate. We wanted in our modelling to be able to have some hard data about how the scapula does move in relation to movements of the arm. Previous data was largely obtained from radiographical studies which were two-dimensional and were not able to record any kind of dynamic motion of the joint together. So the challenges that we had were that we wanted to measure three-dimensional scapular motion, because the motion of the scapula does not happen just in a simple plane, to look at it as a dynamic motion, remembering that the scapula moves beneath the skin, not like some other joints, and so you can't just simply attach reflective markers onto that bone in order to measure its motion. And so some 20 years ago we developed a palpation technique in which a three-legged palpator can be adjusted to fit over the three major bony landmarks of the scapula, and its motion is measured using an electromagnetic motion sensor. And this technique has now been in use for some 20 or so years and still forms an important part of modelling studies. Now we see a graph obtained by a postgraduate, Nicholas Barnett, back for his PhD back in 1996, where he shows this relationship of the major movements of the scapula, the lateral rotation, accompanying abduction of the arm. And we see from here that for about 40 degrees of elevation of the arm, we require something like 15 degrees of scapular motion. It's also interesting, incidentally, to note on this slide that there are measures here of both passive and active motion, so that it appears that there is some kind of internal, what I like to think of as a gearbox, that drives this relationship between scapular and humeral motion, and it still applies whether the arm is loaded or not loaded. So moving on from this simple model and beginning to think about biomechanical modelling, how does this fit in with our main requirement, which is to design joint replacements at the shoulder? If we design a joint replacement, we need to know the loads that are going to be carried by that joint, the range of motion that's going to be required, the range of activities, the usage over the life of the implant, and the environment in which it must operate. And it's towards this aim that the Newcastle Shoulder biomechanical model has been developed over the last several years. This combines some of the kinematic data, that's to say the scapular motion data that I've already shown you, with anatomical data gained from a number of detailed anatomical studies and MRI studies to provide detailed knowledge of the musculature, which can then be attached around the bony skeleton taken from visible human data. And so we see here that the muscles attached all around. These muscles are represented just as simple strings, but the added feature is that when the arm goes through quite large ranges of motion, these strings can wrap around the bony contours to imitate the natural behavior of muscles in a real joint. And so here we see a video of the model with some predicted forces in the video above, and just showing how the whole system works as a complete mechanism with muscles providing the tractive effort. So from this model we can predict forces at the glenohumeral joint, and these are the forces during abduction and flexion expressed as proportions of body weight. So we see here forces of around 80% of body weight during simple abduction. The other data on this slide are from colleagues' work over in the Netherlands, the Dutch shoulder group, who have also, in a relatively similar model, obtained quite similar force levels in their joints. So we have some confidence that we're making reliable predictions. Let's move on now to think about the things that go wrong with the shoulder and how those have to link into the sorts of implants that we want to design. And in particular, we're going to think about inverse shoulder biomechanics. There is evidence taken from a lot of French data over many years showing that in the case when rotator cuff is damaged, those muscles that I talked about, when those muscles are damaged, then there is a superior migration of the glenohumeral joint. If you remember, that fits in exactly with the very simple model we looked at, showing the vital importance of the rotator cuff to maintain stability of the mechanism. It was then the careful thought of Grammont in France which led to one of the original inverse designs of shoulder replacement, in which a complete hemisphere was used attached to the scapula and to provide this reverse articulation, which was found to be particularly stable and successful in these patients. So what are the key design parameters for success of this type of implant? Let's think now about the potential benefits and conflicts of using normal and inverse anatomy designs of shoulder replacement. In the normal anatomy, we have the normal musculature, we have normal scapular motion, which allows that interactions that we've shown in earlier slides. And if we then move to the inverse designs, we're talking about looking at patients who have major problems with the rotator cuff, perhaps almost a complete absence, in which stability can be provided by this inverse design. So, the key features of the normal shoulder and the normal replacement are that there is likely to be complete musculature providing stable motion. There will be normal scapular function, which will allow the ranges of motion we required, and stability can still be provided by the rotator cuff muscles. If, on the other hand, we look at the inverse anatomy designs, the key biomechanical features that we're then dealing with are a compromised musculature in which the rotator cuff is largely absent, a reliance on the deltoid muscle to provide elevation more or less on its own, normally abnormal scapular function, little or no rotator cuff function, and then the use of reverse anatomy, which may in some cases have the potential for impingement problems. In summary, let's look at the overall feelings about biomechanical approaches to implant design. The subtleties of the shoulder complex call for advanced biomechanical approaches to shoulder implant design. In particular, the reverse anatomy of shoulder replacement, while overcoming problems of rotator cuff pathology, calls for sophisticated analysis to minimize the problems of impingement while preserving stability.